Welcome back to TrueNAS Tech Talk. Today, we're looking for your ideas on how to help handle the flash and component pricing crisis that we all find ourselves in. From mundane to madhouse, we want to hear what we can do to improve TrueNAS and help you, the end user, get through these trying times. We're also going to get on our soapbox today about the care and feeding of solid-state drives. What's the right way to take care of your NAND and ensure a healthy and long life? Stick around.
Welcome to this week's show. We're going to want some feedback about what you've been doing in response to the flash and component and other price crises that are going on just industry-wide right now. We're going to have more on that topic at the end of today's show. But before we get into that, we wanted to take some time today and dig into a really cool, great topic around SSDs, flash, what you shouldn't do with them, regards to TrueNAS and ZFS. We saw some very vigorous discussion around this on some of our social channels this week, with a lot of good info, some bad info, and just some downright ugly info that we should probably try and work and demystify a little bit. So Kris is going to walk us through a bit of this today. He spent a lot of time on this topic, I think engaging with some folks as well. So Kris, tell us what we've got right, wrong, and how we need to get people's minds right about how they should worry about flash on their ZFS and TrueNAS system.
Absolutely. I mean, especially with the component prices rising all the time, SSDs is one of those things where, like I said in the title here, it's kind of the care and feeding of your solid state drives. You want to make sure you're taking good care of the components you have, because this is not the time you want to have to run out and buy some new ones because you burned the old ones out. So one of the big topics that sort of brought this up was a topic on our forum that was introduced talking about the concept of sort of charge leakage and charge tunneling with SSDs. This is the phenomenon that over time, the NAND cells, so the capacitive cells inside your SSDs, basically leak the voltage out. The voltage that's programmed into them identifies what bits are in there. It can be as simple as, zeros and ones for single level cell. Obviously, as you put more levels in there with MLC, multi-level, triple layer, and even quad level cells, you have these different number of bits that you can store in there, and you have to have a different level of precision for what kind of voltage you're measuring out of them. And if the voltage drops between those two threshold levels, or between the 16 different threshold levels of a QLC, you could actually get bad data being returned. The challenge there is that as you get closer to the threshold values between them, your SSD now has to try and figure out, hey, was that, 3 ones and a 0 or 3 zeros and a 1, that kind of thing, if it slips between those states. So the idea is this is something that's separate from the concept that a powered off and unplugged SSD will leak its charge in a much faster form of the same degradation. So this is something that maybe those of you who have an SSD in your desktop, hopefully most of you do. If you installed the game many months ago, maybe hopefully now get this is
you
talking
got
about
it before all this happened.
Well, you might notice it because if you bought it a year ago and you installed the game back when it first came out, and you played it with a bunch of your friends. Maybe you played Helldivers when that came out around, almost was that a year ago? I don't remember, but you played it a bunch with your friends, and then you set it down. You went outside in the summer. You touched grass. You went to camp. You did a bunch of things. You came back when the weather got bad, and you fired it up, and you went, well, that's weird. It's loading a lot slower than I remember it. It's almost like you got to dust off the cells of your NAND. So what happened here is some or many of the cells were at sort of those marginal charge levels. They had basically leaked over time. So what your SSD was doing was it was using its in-firmware error checking and correction. It was not only sort of reconstructing that data as it went along, but once it recovers it, it's then got to write it into a new page, a new cell on your NAND. It's not just going to say, oh, I was barely able to read that. Okay, it's fine, but we'll try it again. We'll just leave it as it is.
Yeah. But it's not recharging the existing cell in any way. It's saying, no, I'm just going to make a new copy of it, do it in the background as a copy
That's
operation.
what every SSD works in much the same manner, in this sort of copy on write. They're not going to erase the existing cell and reprogram that exact spot. This is because of something on an SSD called that flash translation layer. When you write to, an LBA on a hard drive, LBA being a logical block address, you're describing a physical location, in the cylinder, the head position, and the sector on the drive. You're describing an actual physical location on those platters. When you do that to an SSD, you could write to that same LBA number 1,000 times and potentially hit 1,000 different pages of NAND on the disk because that SSD is going, well, I already wrote to that one. It's much slower to erase and then rewrite into the same spot. They're just going to say, no, I want to write into an empty space. I'm going to do that. So they'll just write into that new space. They're going to mark the old pages dirty in that flash translation layer, and they'll clean it up afterwards. The challenge is that, reading from an SSD is faster than writing to one. So when you go to read your data and it has to do this error checking and correction, that's going to be slow. Then depending on how your drive firmware handles it, it might say, I'm going to actually write it back to NAND first before I return that positive thing upstream. That could be kind of the slowness. Pretty much every SSD vendor has some manner of error checking and correction in their firmware to sort of detect these marginal charges and recover from it. Some of them even have an idle background media scan or a scheduled active media scan job in their firmware. This is not something that ZFS drives. It's not something that any file system drives.
It's transparent to the OS in that way. This is all copy on writes happening underneath our copy on write on the ZFS side.
We heard you like copy on write, so we copied on write on top of your copy on write. We have a number of things in ZFS that are trying to, mitigate the effects of this write amplification, but you can still see it at times. So the question, of course, people saying, was, well, what do I do about this? And, do I need to do anything? Does TrueNAS, as the developers of us, do we need to program anything into ZFS or our middleware to handle this, to rewrite and refresh this old data that's on the disk? Well, the short version is no, we don't. We have this wonderful technology that already exists called a scrub. And what that's going to do is it's going to go and read over all of the allocated logical space on your drive, thereby reading all of the allocated NAND on your drive that you care about. If there's empty NAND with, blank pages or dirty data, we don't care about that. It's been discarded already upstream from a logical perspective. So when you run a scrub, you're going to go through and your drive is going to basically check at the firmware level first to say, hey, can I read this? So if it's marginal, they'll rewrite it at that point. So your slowdowns that might start to happen, you'll be able to at least sort of schedule that error recovery, and that slowdown time is going to happen during your scrub. And I mean, I know about myself, Kris, but I schedule my scrubs for, the quiet times. They happen at Sundays, 3 a.m.
They happen on Sundays, 2 a.m. my time as well. Again, weekly. Because potentially the more you extend that out on the ZFS scrub side, now it means you may have more of these blocks the firmware has to go repair, and that scrub takes longer. So
exactly. It's kind of like a bizarro world version of trim. You're going through and you're saying, hey, instead of deleting this old data, I just want to check what's there. Now, every time you read from a cell, you do slightly, decrease the voltage level, but it's not the same as letting it sit. And also, it's the advantage of saying, hey, you're being proactive about this. You're checking the cells. You're hoping, like, if you said hypothetically 1% of them were faulty every time and we're at that marginal level, you're recovering that 1% of your data and you're causing that 1% little bit of extra write amplification. Now, what happens if you've somehow, like if you're scrubbing monthly maybe, and some of that data is bad? Well, then you're rebuilding it from your ZFS redundancy. Your SSD will actually say, hey, I tried my best. I can't figure out what this data is. I'm going to throw an uncorrectable read error upstream to ZFS. ZFS will then say, well, hey, this one drive cell said this LBA was bad. It couldn't read it. Reconstruct it from the parity, because everybody's using parity, right? You're not just all out here running stripes. And it's going to rebuild it, send the corrected data back to that SSD, but it's going to program it to a new page. It's not going to send it back to that old page. Your SSD is going to do whatever it does to mark that page as dirty and say, we got to blank this out, and we're going to refresh that cell later. What you don't want to do, so this is important, what you don't want to do is use something like these tools that claim to refresh all of your NAND cells in place. They're built on that faulty premise that an LBA on an SSD is describing an exact location on the NAND. All you're going to do when you use one of those is potentially burn a whole drive write worth of endurance as you blindly read every cell and program it to a new page. That's your best case scenario. At worst, with one of these particular recovery tools or refreshing tools, is it saying it claims to read the data, it inverts your data, so every 0 becomes a 1, every 1 becomes a 0, and it's going to write it back to the same LBA. That's going to therefore refresh the charge in the cell. Well, it's not, because you're writing to an empty page. You're not writing to the same cell you just read from. You're now going to program an inverted pattern to the LBA. Great. So now that LBA thinks it's inverted data. This isn't something that ZFS would detect, because from that thing's perspective, from ZFS's perspective, you told it to invert the data. So it says, I'll install that backwards data. Now you got to invert it again, write your original pattern back to yet another NAND page. So now you've burnt 2 drive writes, and you potentially left your data hanging in the breeze during that intermediary if you have a power outage with one of those inverted writes either committed and not fixed, or in some sort of weird state. So, don't use that. We don't have any technology for that within ZFS. Please don't decide to, once a year, boot up something else that does this, with TrueNAS offline and refresh your SSDs.
Yeah. If that was an important piece
don't.
of what you needed for care and feeding, we would ship it as part of the base system of TrueNAS. It would probably be exposed in the UI as an option. So again, please be careful when you go off the grid like that.
Exactly. Like, the closest thing you have to this would be something like ZFS Rewrite. And the key about that is that anything that you can do that's going to preserve your data integrity of it is also going to cause write amplification, especially if you have snapshots. And people will say, hey, what about copying it from A to B? Well, if you got snapshots, now you're consuming twice the space. Your, block clone might get in the way there, because it'll just say, I'll just iterate the counters on the block reference table, just move it from here to here. It's fine. And you don't actually accomplish your goal. So the short version is just run a scrub, let your drives take care of it.
Yeah. Drive firmware should be doing this properly already.
Exactly. If you have drive firmware that isn't, if you know that you have a guilty party SSD that doesn't do this, then, you may want to look at replacing those. I know this is not the ideal time to do that, but it's sort of a question of data safety. Either that, or you say, well, okay, back up your data to spinning disk. That way, if it does go walking, you can restore it.
Absolutely. Well, how about on the trim side, Kris? How does trim play into this here? Are there any things we should be thinking about with regard to trim on just an out-of-box TrueNAS experience, things we should be tuning differently in an all-flash pool, or are the defaults good?
Yeah. Now, trim was one of those fun things, because back in the day, the default status for trim on TrueNAS, and I believe even in ZFS upstream, was that automatic trim was enabled. Now, trim on an SSD is the idea of it's cleaning up after itself. Nobody likes a mess. As we mentioned, programming into an empty page is really fast. The program cycle on an SSD is quick. The erase one is the one that's slow. It's also much less granular. You're basically zapping the entire page to reset its voltage back to a known empty state. It's one of the things that helps your SSD keep a supply of that clean space. It means your write performance stays consistent. It's one of those things that helps. It's like, managing a hotel. You're not cleaning when a guest checks out, you're going to schedule a time to sort of clean up their room. You're not going to wait until the next guest is waiting at the front desk to check in and then have to run and tidy that room just before they show up. So in general, trim is a good thing. But where you start to hit problems was especially with SATA drives. So in the SATA spec prior to, I want to say version 3.1, trim was a non-queued command, meaning that when you told your drive to trim, clean up a particular chunk of cells, it would have to flush any of the pending IO operations, any pending writes, so that it knew what the state of that block was before it was trying to clean it. So it said, hey, if this suddenly became a valid page, I wouldn't trim it. Or you would be able to tell the controller, hey, stop allocating to here. I want you to clean it instead. So you'd end up with some stalls when you trimmed a drive. And
How
if you had
serious were those stalls?
They could be pretty serious, because, in human times, a millisecond is quick. In computer times, a millisecond is an eternity. we're talking about SSDs that have, program times in the microsecond range suddenly going, well, I'm going to be slowing down to the millisecond range waiting for an IO. That's almost at the level of, network traffic where you say, hey, what happened? I have this great 10, 25 gigabit Ethernet network that transmits at sub-millisecond latency, and all of a sudden my IO times hit 5 milliseconds. Did I buy spinning disks or did I buy SSDs? And this was a challenge that would happen, especially when you had a larger number of disks, because you have a large number of disks in a VDEV or in a pool together. If one of them stalls, your whole VDEV might pause for that 5 milliseconds.
Yeah.
So it's not like you just had a moment to wait.
That makes sense, yeah. And especially because the way the VDEVs work is you do need to have all the drives kind of participating in concert. This isn't a case of we're going to time that one device out and move on. No, it's valid. It's working. We're just going to wait.
Yeah, you just have to kind of wait for it. So the question came up about, hey, let's look at turning off automatic trim. That way, you're basically able to schedule, much like you would with your scrubs, schedule your trim jobs for a period when you expect there to be a lower demand on the IO. You're not going to do it in, the middle of a business day at the 9 a.m. login rush, for an organization running virtual desktops. You're not going to do it during peak order time if you're running a line of business and, you've just released your Black Friday sale. You don't run your trim then. Again, you run it on Sundays, 3, 4 a.m. Your backup jobs are finished. You say, okay, let's go do our tidying. It's like having, again, extending that hotel analogy, you're not instantly sending out housekeeping to do one room at a time and then running back to the supply closet. You're going to kind of schedule it up for that, early afternoon. The majority of people have checked out. There's fewer people. There's less foot traffic. You got the elevators to yourself. Okay, here's the list of, cells or rooms we got to clean. Divide and conquer. Somebody does a floor at a time. You go through, you tidy it up. And that's why it works better. That's why the automatic trim we now disable out of the box on TrueNAS. Most of these issues are limited to SATA drives. SAS and NVMe tends to behave much better with UNMAP and discard because those were queued operations from the get-go. And some of the newer SATA devices, those that embrace the 3.1 or the 3.2 spec, do as well. But it's not universal, and you got to have a controller that supports that dot spec. It's something that isn't guaranteed. So we've talked about everything that works when trim goes well, when all these things behave. So what happens when you have, a drive that doesn't? We kind of talked about this a little bit earlier with specific vendors that maybe their trim didn't behave properly, or maybe they don't have the right things in their firmware. There are a couple known drives, and I'll link to the Linux kernel page for this one, that behave quite badly to various degrees with trim. There were a lot more of them that specifically, when queued trim was introduced, they didn't support it correctly. They claimed they did, but they actually didn't. So it would end up blanking cells that held your valuable data. So what happened was the Linux kernel had to put a flag in the driver under their quirks to say, these drives, even though they claim to support queued trim, they don't do it. I won't call out the vendor. You can see it on the page. It's from one that's more interested in putting AI into their refrigerators these days than apparently coding proper trim support in their firmware. So it's fixed. It's known now. So if you have one of these drives, you're not in danger. But the challenge is when it wasn't known, when you were the early adopters and when you were loading up with these because, hey, they look pretty good, they're cheap, they work great on Windows. Well, Windows wasn't sending queued trim at the time. So
people saw that as file system corruption at the operating system layer, I would assume.
Exactly. They said, why is ZFS having to resilver my VDEVs all the time? The drive says it's healthy. There's nothing wrong with it.
What's going on?
Yeah. Is my drive bad? Or they say, well, it worked fine on Windows. Well, Windows isn't Linux. Windows isn't FreeBSD. Windows is a different beast, unfortunately. There's different drivers going on. And sometimes people like to bag on us, Kris, for saying, hey, you guys have really weird esoteric hardware requirements. Why do you say I can't use this? It works fine somewhere else. Well, it's because of things like this. That's, again, one of the reasons we have our engineering team, our testing team, QA, quality control. We test the crap out of these things. So it's got to handle, the workloads we
Well,
throw at it.
I think folks don't appreciate, Kris, even in the enterprise space, how much you have to do this. I know we've talked a lot about SATA, and this is more kind of the home lab space, but even on the enterprise side, you might be shocked how often we have to go and hold vendors to account because they don't follow the spec correctly, or they put a driver out that has a quirk or an issue or a bug and doesn't behave the way you would expect compared to all the other peers in the industry. That's why vendors like us on the TrueNAS side exist, to go figure out all that stuff so you're not experiencing it in the lab firsthand. Like the manufacturer who likes to put AI in their refrigerators, as you so poetically put it here, because I need my fridge to insult me every time I open it. But anywho,
I can't
there's
let
a lot
you
that
eat
has
that,
to go
Dave.
on. And so a lot of it is not only looking at Linux kernel versions, which version of the driver in that kernel version, do we need to update it? Do we need to pull in patches to, again, work around a quirk, which is a way of saying we didn't follow the spec fully on the hardware side.
That's kind of one of those things. Sometimes, though, the spec is really weird. And there's one more thing with trim that has to do with, it's called deterministic zero after trim. So DZAT, or, return zero after trim. Basically, this was something that those of you using a home system with an LSI HBA, good on you, by the way, you probably encountered this when you put a bunch of SATA SSDs behind here, because that controller wanted to say, hey, you need to guarantee to me that cell got erased before I'm going to allocate to it again. And there were certain SSDs that were very good about this, but the spec didn't actually demand this with trim. It said, you can do it if you want. So there were a couple vendors, Micron, Intel, Samsung. They were good about this, and they would actually reliably return that zero. Other SSD vendors did not always do that. So people would put their SATA SSDs behind their SAS HBA, and they'd go, hey, why is this slowing down? How come trim's not working? And it was because the controller was looking for a part of the trim spec that wasn't implemented in your drives. So this comes to one of those weird sort of Kris's esoteric rules of thumb about SSDs. I try not to buy them from someone who doesn't make their own NAND, or at the very least, make their own controllers. So, I mean, all the SSDs that I have in, kind of my TrueNAS setups, I think come from 4 vendors. They come from Micron, Intel, Phison, and some old HGST stuff. They don't make them anymore. So those are the ones that I buy.
You don't go to the
from
alphabet soup you find on Amazon when you type in, M2 SSDs, and you get all these companies.
No.
You're like, man, there's 22 company names I've never heard of until this very moment.
If the vendor name looks like I rolled my face across my keyboard and hit enter, I'm probably not going to buy the SSD from them. If I do, I'm not going to consider it for anything really valuable. I probably won't even use them as a boot device. Heck, I managed to burn out an Intel SSD as a boot device because it was a consumer one. I've since replaced it with a little SATA Enterprise SSD, get them fairly inexpensively secondhand. It's still got a lot of life left with it, and I imagine it's going to be much more reliable than that one was before. Yeah. All right. One more.
What other alphabet soup do we have to worry about here?
One more. So when we get into the alphabet soup, we're usually talking about when people start looking at SSDs for SLOG devices, separate logs. So they're saying, hey, I actually do sync writes on my pool. I need to put an SSD in front of here, and I want to put one in there to make things fast. So they go out and they'll say, oh, this SSD says it does 3 gigabytes or 7 gigabytes a second. I'm going to put it there, and that's going to be the best possible log device for my pool. And then they get very surprised when that SSD is nowhere near as fast as it was. So this is where the alphabet soup comes to the letters PLP, for power loss prevention. And it's crucial. Now, most SSDs do power loss prevention, but they will only protect the data that's at rest on the SSD. So they say, hey, when the firmware is in the middle of doing some of that reprogramming of pages, like we talked about earlier in the episode, where it says, hey, this cell was marginal, I'm going to read it, I'm going to write it back to a good spot, and then I'm going to return it. That's the idea of sort of that power loss prevention. It's guaranteeing that I'm not going to wreck data that's already been put safely to your SSD. What you need for a log device is power loss prevention for data that's in flight. So when you accept those writes into a DRAM buffer or a temporary area of your SSD, you have enough power loss prevention, usually done with little tiny supercapacitors on the drive, to say, if you yank the power from the system or even hot plugged that drive, if it's a supported chassis, it will actually commit all of those pending writes in its DRAM buffer down to stable storage on NAND. That's what you need for a fast log device. We had a real big thread on the old forums going, but it kind of stopped in the era of when NVMe was getting really popular. I think back in the day, it was, we'd settled on Optane was the big one. And unfortunately, Optane's not made anymore. So
this was akin to what we did with NVDIMMs back in the day when we were shipping more of those, which was the idea of you have a stick of RAM, it has a super cap attached to it somewhere, and then the ability, again, God forbid the power get pulled suddenly, to still take that active state that's about to be lost, enough power left to flush it to the persistent memory and survive. So
exactly,
just happening all inside your drive now.
And when people talk about, the power being lost, they'll often say, well, I don't need that. I have a UPS. A UPS is great for handling brownouts. It's great for, having a single power supply and somebody trips over your plug, but it doesn't stop the power supply itself from failing. Doesn't stop your HBA from dying, your motherboard, your CPU, and it doesn't do anything about kernel panics. If you happen to somehow get one of those, you find an exciting new edge case bug. That's still going to break things. Even if you have all those things, it works properly and you lose power. If your system's still running because it has that UPS, it's still accepting I/O. ZFS doesn't know it's on a UPS. Until you export that pool, you're still potentially putting data into that next open transaction group. So, because your SSD doesn't know that you have some holdup power, it doesn't know to immediately, cut power. Maybe you can say, after 30 seconds, it's going to shut down. Well, that's great. So that's still 30 seconds of exposure. And it's also your ZFS still saying, hey, I don't know there's a UPS in there. Yeah. I still want you to flush.
I'm still open for business.
Yeah. Yeah. So that's one of those things where if you need a log device, you do have to go with, like I said, those weird requirements that we have, definitely not founded on thousands of testing hours and lots of very painful experience in our past. Again, we make all these horrible mistakes in a lab. We experiment. We find the sharp edges. We're the first ones down the ski hill. We've found the pointy rocks. You don't need to hurt yourself on them just to find they're there. We're trying to put up as many signs as possible.
Yeah. And then we go have the in-depth conversation with the highly technical hardware engineers and firmware engineers to get clarity and understanding on there's this weird behavior we can't quite explain. Why? Yeah. Why does that happen? What do we have to do to mitigate or work around it? Is it at the OS level? Or are we talking driver changes, firmware change, like all that stuff? It's fun. Keeps us all busy.
It is. And then we get to take all of this wonderful information and we get to share it with you, the listener, on the podcast, who's hopefully still tuned in at this point, and I haven't put you to sleep. And if I have...
No, our crowd likes the technical stuff. This is good. This is good. We need to do more of this.
Well, I'm glad. So, speaking of technical things, Kris, you mentioned it earlier in the episode. We were going to talk about, what can we do from a technical standpoint to say, hey, how can we alleviate some of this pain? Some of it obviously would be, what can you do with the stuff you have, which was the point of this whole episode. But you said, what sort of, new things do you want to do?
Yeah. So this is one of those things. We're looking at the industry as a whole, and we're seeing the crisis. We're seeing the crisis in flash prices and memory prices. You've seen it in price, all sorts of things. Even other components now that you wouldn't maybe have associated with that originally might see their prices go up, or scarcity becomes a real thing. So we're getting creative. We've talked a lot last week about the TrueNAS 26 version on tiering between flash and spinning, and the idea of having a hybrid pool, or maybe you can't afford to go all flash because it's too expensive, not available. So you're going to need to be in that hybrid state for a while. But you have certain use cases where you do need flash performance, and others where it's like, no, I can throw that to the spinning and life goes on. Yeah, those are things we want to do in TrueNAS 26, and we are doing, which will be great. But, we're taking a look at this and saying, okay, this is an interesting, moment in the industry, and it may last a while. What are some other more immediate things we can do, maybe short, midterm, to help alleviate some of the challenges we're going to see on the hardware and supply side? So we're looking at all options. We got a lot of things on the table to consider here. But I wanted to take a moment to throw it to our awesome viewing audience because you guys are also highly technical. And in many ways, we're all solving this in our own ways, in our own environments. It might be you're a home labber and you're really technical and you just do this for fun. You might be having to solve this in different ways at your business or enterprise as well. I'm curious to hear from you. This is your chance to provide feedback. What are some of the strategies you're adopting for dealing with this? And are there things on the TrueNAS side that would help make those strategies easier to roll out, easier to deploy or support? So again, I'm open to all kinds of ideas here. And we're even thinking big and unconventional. I mean, we could get sacrilegious and say things like, should we more actively support USB as boot media again, so you don't have to sacrifice a U2 flash device for the boot image? Maybe that's a thing we should consider. Again, it doesn't mean all ideas will be accepted, but I love to hear them all because you never know when that crazy idea sparks something else and you go, that's not half bad. We could probably do something with that and iterate on it. So again, throwing the floor open. We want to hear comments from you. And maybe next week we'll devote some time to some of the better ones and get some creative juices flowing around that. Because one of the beautiful things about TrueNAS is you can have a relationship. You can go and talk to some of us who work directly on the software. We engage with our community on the forums, on the open source site, on GitHub, which is pretty cool. And so we like to extend that warm welcome and open the door and tell people, hey, a lot of ideas are welcome here. We can't promise we'll go do them all. Time, resource, money. If I had infinite developers, of course, we could do infinite ideas, but you never know who's going to have that creative spark and come up with something that's really, that's a great idea. Why didn't we think of that before?
Exactly.
So again, throwing the door open. Love to hear what people got.
Even if you think it's kind of a silly idea, if it's ridiculous and it works, was it actually ridiculous?
I have a philosophy, and frankly, it's how I do my best work too, is I like to sit and just think out loud and throw crazy ideas on the whiteboard. Because what I've found is, at least for me, and maybe some of you can relate to this, is you throw 20 crazy ideas out, and then all of a sudden you start to hone in on a couple of them and you refine them. And then at the end of it, you're like, oh, that was the spark of a very not so crazy idea, which is actually a very good idea. It just needed that creative process to go through as you kind of chip away at the edges and sharpen it a bit. And all of a sudden you took something that just seemed wild and far-fetched. Who in the right mind would suggest that and throw that on the whiteboard too? That's a feature. We should go implement that. So anywho, again, maybe you guys think the same way. I'd love to hear it.
Absolutely. So looking forward to those questions, considerations, crazy harebrained ideas. I certainly have a few of my own that I'm sure that Kris and the engineering team are already cringing, imagining what I'm going to throw into their GitHub PR shortly.
Absolutely. I can definitely make a lot of engineers cringe. But again, you never know. If you have 100 ideas, 10 of them are great. That's 10 more than you had if you didn't try. Okay. Well, thank you very much, Kris. That was an awesome technical deep dive. Looking forward to hearing some commentary on that. Maybe it spawns a whole nother forum thread. We'll see how much people want to argue with you.
Well, I always welcome the conversation. Whether you want to have it on the forums, have it in the comment section below, please continue the commentary. We love the discussion and we love the engagement. So with that wraps up our episode for this week. As always, thanks for tuning in. We appreciate all the subscribers we have. We're over 4,000 now by a healthy margin. So thanks for making this something that Kris and I can do every week and enjoy. If you have any further questions, comments, again, drop them in the comment section below. Jump over to our forums at forums.truenas.com. Make sure you do the usual YouTube things, like, subscribe, ring the notification bell. Don't forget to reach out to us at t3@truenas.com, and we'll see you again next week.